Thank you everyone for joining this distinguished webinar series in AI and Cybersecurity hosted by Center for AI and Cybersecurity at Ph.D. And today's talk is about the title towards reliable NISQ system, which is basically noisy intermediate quantum systems. And it's my pleasure and distinct honor to introduce Dr. Samah Saeed from City University of New York for this webinar. Dr. Samah is an assistant professor in the Compilation department at Brownstein and CCNY, City University of New York. She received her Ph.D. in the Computer Science and Engineering department, New York University Tandon School of Engineering. Her research interests include the security and reliability of quantum circuits, hardware security, and testing of VLSI circuits. She is the winner of the Best Paper Awards for multiple conferences, IEEE VLSI Test Symposium, the Brownstein Doctoral Research Award at NYU Polytechnic School of Engineering and TTTC. McCluskey Best Paper. Her research is funded by DOE. She has served as session chair and moderator for conferences in the IEEE and a lot of conferences to talk about very so there's prominent conferences like European Test Symposium, International Conference of Computer Design, Quality Electronic Design. She also served as program committee member for multiple conference, Design Automation Conference, Computer Society, and Symposium VLSI, and European Test Symposium. So it's a very relevant reference to circuit design. And she has organized a special session on topic towards efficient testing of AI accelerators for IEEE VLSI 2022. As you can see, that's quite a amount of service activities and the prominent revenues that Dr. Samah has published. And it is my distinct honor, Dr. Samah, for your time and effort that you are putting together for this webinar series. And the floor is yours. Thank you so much for sharing your insights.
Thank you so much for the introduction. Let me share my slides too. Okay, so can you hear me?
Yep, we can hear you, Dr. Samah.
Okay,
yep.
Perfect. Thank you so much for the introduction. So today my talk is under the title of Toward Reliable NISQ System. So in this presentation, we will look into some of the main challenges to enable quantum advantage. We will also talk about some of our research efforts to counterpart these challenges with particular focus on the role of machine learning to enable reliable quantum circuit execution. So first, I would like to take the chance here to thank our collaborators, sponsors, and of course, the students who make things happen. So in our research group, we look into different problems from the system to the device level, with particular focus on three different research thrusts, which are hardware security, testing integrated circuit, and secure and reliable quantum systems. So when it comes to hardware security, we focus on different side channel attacks, and we look into solution both at the software and the hardware level. With manufacturing testing, we are more interested in making the manufacturing testing process very efficient in terms of cost, power consumption, and performance. And for the past 2.5 to 3 years, we started to look into secure and reliable quantum systems. And today I will be focusing more on the reliability aspect of these quantum devices. So this is the outline of my talk. First, I'm going to give a brief introduction about quantum systems. Then I will look into the design flow of quantum circuits and talk a little bit about the compilation stacks. I'll discuss some vulnerabilities and reliability issues. And I want to shed light on some of our recent proposed work toward detecting error drift and modeling failure of the quantum hardware, and leveraging these models into the compilation stack to mitigate errors. And then I will conclude my talk. So while quantum physics was out there for so long, the concept of quantum computing was proposed back in 1982 by Richard Feynman. And his idea was, as we don't have a clear understanding about the quantum phenomena, why don't we build a quantum computer that simulates the quantum physics? And after that, we start to see very interesting applications looking into how do we take advantage of these quantum devices. One of these killing applications is factorizing large number in polynomial time, which is known to be short algorithm that threaten most of the nowadays encryption algorithm, particular focus on RSA and AES. And that actually the reason why motivate a lot of works related to post-quantum cryptography. But having said that, there are also very interesting and useful applications for these quantum devices, such as searching in big database, which is polynomially quadratically faster than classical computers. Also, we can think about it as a tool to help us to discover drugs or study climate change using quantum chemical simulation algorithms. And one of the hot topic nowadays, how do we use quantum computers as an accelerators for machine learning using quantum machine learning? And because of all these useful applications, we start to see both big players and startup companies working in building quantum devices. In all these companies, the business model is you have a centralized quantum device that is accessed remotely through the cloud by different users. The reason why the quantum hardware is supposed to be centralized because of the complex control systems and also the restricted control environment for these quantum devices. And you must also have heard recently, back in 2019, Google quantum supremacy article in which Google claimed that they achieved quantum supremacy by executing these large quantum circuit in a 53-qubit quantum hardware. And while there is a lot of doubt about whether Google were able to achieve quantum supremacy, this by itself shows you that we are actually progressing in building reliable quantum hardware that somehow very close to achieve the quantum advantage. So currently, we are in what we call the noisy intermediate scale era, or the NISQ era. This is a terminology that was proposed back in 2018 by Briscoe, and it refers to quantum devices with limited number of qubits. We can say tens to hundreds of qubits that are noisy. And because of the small number of qubits, we cannot apply error corrections. And instead, we have to think about how do we mitigate errors. And so how do we build error mitigation techniques? And some of these potential applications for these NISQ devices are solving optimization problems using hybrid classical and quantum algorithms. And so let me talk about the main physical constraints at the architectural level for these quantum devices. So we have the coupling constraint that determine the qubits that can directly interact with each other. And this coupling constraints also depends on the underlying technology. So if we're looking into superconducting quantum devices, such as this example for an IBM quantum device with 5 qubits, we already have limited qubit connectivity because of the crosstalks of the qubits and the hardware level. Versus if we look into trapped ion quantum system, for example, all the qubits can directly interact with each other. Of course, there are other constraints such as the gate time or the operation time, which vary from one qubit to another. Qubits are susceptible to different types of errors, including the gate errors, which could be either single or 2 qubit gate errors, or even the readout errors that occur when you measure the qubit states. And then we also have the coherence time that determine how long the qubit can retain its state. So from the architecture level, we can think about it as a retention time. And it's classified as relaxation versus depressing time. We also have crosstalk errors. So if you apply at the same cycle or at the same layers, different operation on independent qubits, they may cause interference and result in crosstalk errors. So in order to characterize all these errors, we calibrate the hardware periodically, sometimes daily, depending on the hardware, sometimes even multiple times a day. And we apply different protocols to characterize the errors during the calibration process, such as randomized benchmarking that help us to compute these error rates. And so when you look into these gates and measurement errors, we consider these as active errors because you're applying certain operation to the qubit, versus these decoherence and crosstalk errors can result in idle error because they can also occur when the qubit is idle and there's no operation applied to that particular qubit. So let's talk about the quantum circuit design flow. So the input to the quantum systems is nothing but a quantum circuit that consists of gates which operate on qubits. And these qubits could be either in a 0 or 1, or maybe a superposition of both. Now, when you think about the gates, it's nothing but a manipulation to the qubit states. So it is a unitary matrix, and all that it does, it rotates the qubits around the X and the Y and the Z axis. And you can think about single qubit gates and multi-qubit gates, such as CNF gates. And we also have measurement operations that help us to collect the output of the circuits. So in this slide, I'm showing you a subset of the quantum circuit compilation stack, where the input is a logical representation of the quantum circuits, as well as these physical constraints of the quantum architecture that we talked about. And so we apply a series of compilation steps to generate a circuit that can directly be executed on the hardware. So this involved gate decomposition, which takes complex unitary gate and decompose them into elementary gates supported by the architecture. And then we apply also a series of optimization steps in order to reduce the gate count and the circuit depth. So one example you can think of pattern matching approach that looks into cascades of quantum gates and then replace them with a smaller subset of gates that is proven to be equivalent to that patterns that you identify. Also, you can think of, for example, rescheduling gates so that you can cancel as many gates as possible. And the last step here is we map this logical circuit to satisfy the physical constraints of the quantum architecture. And so I want to spend a little bit more time talking about quantum circuit mapping, because it's a very critical steps that significantly affect the output state fidelity of the quantum circuits. And so the idea here is we want to generate a physical quantum circuit that minimize as much errors as possible, which is equivalent to maximizing the success probability of the circuit. So as you build these circuit mapping, quantum circuit mapping algorithms, you need to have an objectives or you need to have an objective which define your success matrix. And typically, people use an estimated success probability. It's a very simplified success probability matrix that looks into the calibration error rates of the gates, multiply them together, and also looks into measurement error rates that are used in the circuits, multiply them together with the restriction that the circuit depth should be less than or equal to the minimum coherence time of all the qubits. And so if you look into this logical quantum circuits, I can generate this corresponding physical quantum circuit by first allocating physical qubits and also determining next the qubit movement. And as you can see here, we introduce a new operation, which is a swap that enable logical qubits that do not talk to each other to be able to talk to each other, basically. And so one of these main challenges here, when we start to think about how do we generate the quantum circuit mapping, is the absence of an accurate failure model to capture temporal and spatial variation in errors. So we use the simplified estimated success probability, but it doesn't really capture the actual failure in the hardware. And so let me talk about the vulnerabilities and the reliability issues in the quantum architecture. So here, I'm giving you an example of IBM Q Melbourne quantum architecture, which consists of 15 qubits. And you can see here the Vazirani quantum circuits. We generate the corresponding physical quantum circuits here by conducting the mapping, and we allocate initial qubits, which are M1. These qubits tend to have, the lowest error rates in this architecture. We can also generate another physical quantum circuit by allocating another subset of qubits, which we call it M2, marked in this pink color. The main difference between these two qubit allocation is that M2 has significantly higher error rates compared to M1. Now, because both M1 and M2 are considered as isomorphic subgraph, the corresponding physical quantum circuit will share exactly the same circuit structure. So we'll have the same structure, the same number of gates. And so if we run both circuits on the quantum hardware, we would run each circuit for a large number of time, and then we would look into the success probability, or we would look into the output patterns with the highest success probability. And as you can see here, M1 will provide you a result, which is all 1, which is actually the correct output of the circuit, versus M2 will give you as the expected output 0, 1, 1, 1. So this is a very simple example that shows you the impact of the qubit allocation on the success probability, or let's call it the fidelity of the quantum circuit. Now, this could be a very big problem from a reliability perspective, especially if there's some sort of error drift within this calibration window and before you conduct your next calibration. That means that your resulting circuit would have very low success probability, or it may generate incorrect result. This could also be a problem from even a security perspective. If there is a malware, for example, in the quantum compiler that try to manipulate these error probabilities so that at the end of the day, the resulting circuit will provide you incorrect results. Or even you can think about it as a rogue element in the quantum computing companies, which report these calibration data. If they want to specifically, for example, produce some incorrect result for a certain application, they can just simply manipulate these error rates, and that will directly lead to some incorrect results. And so our target here was, can we do a runtime monitoring, and can we evaluate whether we trust these backend properties or not by ourselves? And so we proposed back in 2020 to online monitor a quantum circuit by generating what we call test circuits. And so the idea here is you're going to compile the circuit, generate the corresponding physical quantum circuit, and then you will start to inject test points that helps you to study the error rates at different points of the circuits. And then you can look into another subset of qubit that tend to have the highest error rates. And then you can inject exactly the same test circuits and then execute all these circuits on the hardware and conduct some analysis to study whether these calibration error rates are accurate, whether there was some error drift within the calibration window. So let me just talk about this a little bit more detail. So one of the key advantage here is we don't have to change anything in the quantum circuit design flow. We can easily integrate these test points on the, or let's say add them on the physical quantum circuit after conducting the quantum circuit mapping process. And so when you try to inject test points, your objective is you want to cover as many circuit errors as possible. So you want to cover as many gates and regions in the circuit as possible. And so we generate a test point with two main requirements. The first requirement is we want to ensure that the test circuits give you known results. And this is simply because we don't want to rely on any simulator, because as you know, as the quantum circuit size grow, then we cannot actually start to simulate the circuit, because that's the whole point of using the quantum device. And the other thing is, if we create these test circuit, and if for any reason we have to use some sort of entanglement or 2 qubit gates, we want to make sure that these 2 qubit gates satisfy the coupling constraints of the hardware. So the cost of the test circuit itself should be as minimum as possible, so it doesn't interfere the errors with the errors of the actual circuit. And so we consider 3 types of the circuit. The first one is like the simple classical test that checks that the qubit is in a classical state. So this is very useful for auxiliary qubits and helper qubits that are used in different applications. They're also useful for any qubits that are used in their initial state as well, before you start to apply any quantum gates. And then we also look into superposition test, and this test, as you see here in the slide, is actually inspired by a superposition assertion that was proposed a few months earlier. And the idea is that they built that superposition assertion to check for design bugs in the quantum circuit. So we leverage the same concept, but to test for errors in the quantum hardware. And the last type that we actually propose is to use the concept of uncompute. So we already know that the gates, regardless of how many gates we have, they are just simply a unitary matrix. So if we apply the inverse of this unitary matrix in a reverse order, then I guarantee that U multiplied by U inverse will always give me an identity matrix, and therefore the measurement will always going to be the initial state of the qubits. And so when we build these U inverse, we ensure that U plus U inverse, or let's say we ensure that the depth of the test circuit is less than or equal to the minimum coherence time of the qubits, again, because we don't want to introduce additional decoherence errors. And so this is just an example to illustrate how these test points look like. So this is an example of the Zrani quantum circuit. Again, we can do a classical test by conducting a measurement of the qubit in their initial state. We can test the superposition state of qubit P4 after it is swapped. So you can conduct your test at this point. And then we also have here the uncompute test, which simply, for example, tests this region by applying the inverse of the gates in a reverse order. And so once we generate these test circuits, we start to think of the comparison, right? So the circuit mapping the quantum circuit mapping generate a physical quantum circuit that leverage these qubits. And so we search in the coupling constraints of quantum hardware into an isomorphic subgraph, right, that share exactly the same structure, but has the highest error rates based on the backend properties using the estimated success probability metric. And then we take the two quantum circuits and inject exactly the same set of test points, and then we start to analyze. And then we start to execute, these test circuits on the quantum hardware. And so the analysis part, we look into how many of these test circuits under the green qubit allocation give you better results than the test circuits under this pink qubit allocation. And the expectation is that most of the test circuits from the good mapping should give you a better result than the bad mapping because they do have a higher success probability. And if this equation doesn't match, that means that either there's error drift or there's some manipulation in the quantum hardware error rates. And so we try to justify this by running the good circuits and the bad circuit with their test points in IBM-Q Melbourne quantum hardware. And we reported this percentage of good circuits, or let's say test circuits under the good mapping that gives you higher success probability than the bad mapping. And in this example, all of these probabilities are even higher than 50%. And when you look into the actual the circuit execution, which is the physical quantum circuit under the good mapping versus the physical quantum circuit under the bad mapping, you see that the good mapping circuit always give you the highest success probability. In fact, we also have some other results where sometimes these pink bars give you higher success probability because there's some error drift. But then at the same time, this probability from 70% will drop down to 30 or 10%. So that gives us more indication that yes, these test points are actually helping us to decide whether we should just take these physical quantum circuit implementation based on the calibration data, or maybe we should either recalibrate the hardware or re-implement the physical quantum circuits. But one of the things that we thought is a little bit problematic is that we have to also compare against some other circuits which tend to have like higher error rates. So that means we have to conduct so many executions. And that's something that makes us think of why don't we build an ML model that actually look into the physical circuit and their test circuit and just predict the fidelity right away. And so before I talk about our model, I also want to talk about one earlier model, ML model, to study the reliability. So it came 1 year earlier by Lu. And the idea here is they consider the quantum hardware as just, or the quantum computer as just a black box. And they just execute some random circuit and they look into the output of the circuit. They take the random circuit and their output, and they train an ML model to predict the fidelity. Because the quantum hardware is a black box, that means that they don't look into the calibration property, they don't look into the backend feature reported after each calibration data. And the downside of this is that every time you calibrate your hardware, you have to retrain your model. Because the physical, I mean, the coupling constraints will stay the same, but these information about the gate error rates, even the gate time, the coherence time, these information vary from one calibration window to another. The other downside that we looked into is that if there was some error drift within the calibration window, then this model may not be able to accurately detect it because it simply takes like a very general handcrafted structure and feature of the quantum circuits to build the model. And so we looked into an ML reliability model that takes advantage of the structural features, in addition to that, the backend feature, as well as the test circuits. And so we take the logical representation of the quantum circuit, we feed it to a quantum compiler, and then the resulting circuit is the resulting physical circuit is used to extract circuit structure and feature. And then we also look into the backend feature during which you will execute the circuit during the training phase. And we extract some backend related features. And then we start to generate some sort of test circuits, execute them on the hardware, and we extract the properties of these test circuits, primarily the results, and use that to generate test features. And then this feature vectors is used to train an ML model to predict simply the fidelity. And so we can use even very simple machine learning algorithms. And the training data set is created based on random circuits. In fact, it's created based on two types of random circuits. So the first one is random circuits that include universal gates, which are followed by an uncompute operation. Because again, when you conduct the training, you want to know in advance what the output of each circuit is, in order to be able to assess the fidelity of the output. And so this is one example of one random quantum circuit where we apply some gates and then we apply the inverse of the gates to ensure that the output is 0. So we also apply the concept of uncompute. But these type of circuit will always going to give us a single output. And so we also wanted to have these circuits that generate an output distribution with, the correct result is an output distribution, because that's very useful if we look into near-term quantum algorithms, such as solving optimization problems. So we don't have a single output, we have an output distribution. And that's why we use a specific class of quantum gates. We call them Clipper gates. These are very efficient gates in the sense that they can be efficiently simulated using a classical computer. Having said that, using Clipper gates only, you cannot really achieve any quantum advantage. So typically you will have other universal gates in your circuit. But for us, since we are more interested in studying noise, we just built circuit based on Clipper gates. And yes, you will get a correct and expected output, which is an output distribution. And we can use that also to assess the fidelity of quantum circuit that do not evaluate to a single output. So you take the random circuit and then we actually generate two corresponding versions of this random circuit. So we look into physical quantum circuit that use these qubit that has the best properties in terms of errors. And then we look into qubit that has these bad properties. And this is basically to ensure that we have a diverse training data sets, because at certain days, all the qubits will have very bad properties. So you should be able to predict. And so this is one of the results. again, we trained the model for IBM Melbourne. So I think we collected data sets for around a month or so, and we had like around 2,000. Sorry, we have around like 2,000 data sets. And so what you can see here in the y-axis, we reported the difference between the estimated fidelity. The fidelity metric here is just probability of successful trial, because all these circuits evaluate to a single output. And the observed fidelity, meaning that when you execute the quantum hardware, what was the success probability? And as the difference becomes, as you minimize the difference, that means that your maximum, that means that the model is very accurate. And so we compared the machine learning model against this ESP that I mentioned a few slides earlier. It's the estimated success probability, the simplified matrix in which you just multiply error rates, as well as the Qiskit noisy simulator. So Qiskit is an IBM platform that also support noisy simulation of quantum circuits. So they basically conduct a classical circuit simulation, but they take also into account these error rates reported at the calibration data. They have a mathematical formula of how they actually introduce these error rates into the matrix multiplication, like into the simulation process. One of the, you can think about it, one of the limitations here with the simulation is that, as the number of qubits grow and as the number of qubits increase, the simulation will be kind of harder to achieve because they rely on classical computing. But even though we were able to run the simulator perfectly, you can see that all the ML model here gives you very high accuracy compared to the white and green bars, which are the noisy simulator, as well as the estimated success probability. Okay, and so the next few months after, I guess the next year, we start to think about, okay, this machine learning model is quite useful, but then we have to interact with the quantum hardware. And we have currently very limited interaction with the hardware. And more importantly, when you do the uncompute, there is an additional overhead because of all these inverse gates, like the U inverse that you apply. And this U inverse by itself may introduce also additional errors. And so we were looking into how do we build a model that is cost effective, meaning that it doesn't require any hardware interaction, and also accurately capture the circuit structure and give you very high output fidelity. And so in our TCAT journal, we looked into using a graph neural network to model the reliability of the quantum circuit. Why did we use graph? Because the physical quantum circuit is simply nothing but a graph where actually nodes are gates and the links between nodes are just direct dependency between gates. And so you can now capture the circuit structure using the graph, and you can add feature vectors that capture all the features of every single gates in the circuit, including the gate type, the number of qubits, the qubit ID that operates, that the gates operate on, the gate errors, the qubit coherence time, and so on and so forth. And so then what we do is we conduct the node embedding, where we aggregate neighboring node features into the target nodes, and then we apply the graph embedding, and finally we generate the fixed feature vectors in which we run a regression model. So I want to skip the details here for the time constraint, and I just want to show you one of our experimental results. This is actually on a different quantum device. So this is an IBM Guadeloupe, which has 16 qubits. Again, we run the previous machine learning model. We also include graph neural network, and then the Qiskit noisy simulator and the estimated success probability. Again, all these traditional ML models require interaction with the quantum hardware prior to the inference, versus GNN model doesn't need any of that. So you just feed in the circuit, and we extract everything that we need, including the data dependency graph, and we just conduct the prediction locally offline without any interaction with the hardware. And so, as you see, the red bar here represent the GNN inference like accuracy, and as you can see, it always give you the highest prediction accuracy without any interaction with the hardware. Okay. So that was interesting. The next question, I guess the logical question is, it's good that we can model errors, but can we use that to maximize the success probability, which is going to be more useful, I think. And so how do we leverage these neural networks to mitigate errors? And so with that, I particularly give you one use case of another work that we did last year in ICCAT, where we looked into the problem of idling error mitigation. And so we already talked about idle errors. These are the errors that occur in the qubits when it is idle, right? And experimental physicists, they have looked into how do we leverage something called dynamic decoupling to mitigate idling errors. And so the idea, during this idle qubit window, you can apply a sequence of single qubit gates. These single qubit gates eventually evaluate to the identity gates, so nothing really will change the functionality of the circuit. But because you're doing so many rotations to the qubit, eventually that should suppress idling errors. And then the question is, how do I generate these single qubit gates? And so there were several proposed methods from theoretical physics to implement these dynamical decoupling sequences. So we focus on the XY4 protocol because it has been tested with these IBM quantum devices and it shows to be useful and effective. And so here the sequence, one sequence or one DD sequence consists of XY gates. And so if we look into this quantum circuit, particularly qubit 0 is idle for around 547 nanoseconds. And so there is some sort of an idle window here. And given that the DD sequence consists of these 4 gates, these gates will take around 210 nanoseconds. And that means I can apply 2 DD sequence within the idle qubit window to mitigate idling errors. So then the question is, why do we need error mitigation? Like, why do we need a graph neural network? And so a very interesting study was done back in 2021 in Micro that shows if you apply these DD sequence in all the idle qubit windows in the circuit, it doesn't really guarantee for you that it will improve the fidelity. So sometimes you apply them everywhere, and then the fidelity will stay the same. And in fact, we extended this analysis by looking into different combinations of these DD sequence. And we realized that there are also certain scenarios where if you apply these DD sequence, you can even reduce the fidelity compared to the base case where there's no DD sequence. And so what they actually proposed is an adaptive approach based on similar concept to test. So you're going to generate some circuits, execute them on the hardware, and based on their result, you will decide where to insert these DD sequence. So to be more accurate, if this is your input circuit, you will generate a lookalike circuit that share exactly the same structure, but use different gates. Again, these are Clifford gates simply because we can easily simulate the circuit. We cannot simulate the circuit. And we have to know what the expected output to be able to tell the fidelity. So we generate a lookalike circuit and we inject different combinations of DD sequence. We execute them on the hardware, and the circuit that gives the highest success probability will determine where do we insert the DD sequence in the original quantum circuit. So this work was very efficient actually, and it shows some improvement in the output state fidelity. One drawback, of course, the search space was very limited. If you can think about the idle qubit window, if you have a circuit with n idle qubit window, you can have 2 to the power n possible combinations of DD sequence, and you can do that. So they restrict their search space in a very narrow. So they exclude so many cases to be able to come up with a feasible number of test cases, which is fair enough. But the other issue is that all these analyses are based on decoy circuits, which are not actually the original circuit. And one thing about DD sequence is that their impact on the circuit also depends on the qubit states. And now, I mean, yes, they try to approximate, to have an approximate algorithm that generate Clifford gate that's somehow very close to the original circuit, but they are not the circuit themselves. And so, like I mentioned here, so we try to expand the analysis, just start to understand what happens if we expand the search space, if we look into different combination of DD sequence. And we looked into two different quantum hardware, which are Guadalupe and Lagos. And we generate really large number of circuits. And we start to see as we expand the search space, we can even achieve more than 10% increase in the output state fidelity, not compared to the base case, but compared to that approach that we discussed earlier. And so we start to think about what can we do better to improve the output state fidelity, and how do we leverage our deep learning model that accurately predict the fidelity of the circuit. So our objective here is insert DD sequence in the quantum circuit, which improve the output fidelity. And so we say that the problem of searching for DD sequence is analog to identifying the criticality of idle qubit windows. And so if I can determine this idle qubit window is very critical, then that means I have to insert DD sequence. And if this idle qubit window is not critical, then I shouldn't insert anything on it. And so we use here a node classification graph neural network that help us to classify idling errors to be critical or not. And so just to give you a good idea of what we're doing. So as we said before, we construct a gate dependency graph of the quantum circuit, and then we introduce what we call it virtual nodes. So we look into the location of these idle qubit windows, and we represent them as virtual nodes added into our data dependency graph. And then we start to do this node embedding for each target node. And eventually, we will apply the node classification on only the virtual nodes. And so for each virtual node, we predict whether it is critical or benign. And eventually, if the node is critical, we will go to the corresponding idle qubit window and insert DD sequence. Otherwise, we leave it idle. And so when you think about feature vectors, they're kind of similar to what we discussed in the reliability model, with some few additional features. So obviously we need a feature that distinguish physical nodes from virtual nodes. So gates from idle qubit windows in which we can insert DD sequence. And then we have this interesting feature, which is the measurement probability, because the impact of DD sequence depends also on the qubit states. And we don't want to rely on simulation, of course. We started to think of, why don't we approximate the magnitude of the qubit state? And this simply can be done by injecting a measurement at the beginning of the idle qubit window. But then the moment you talk about measurement, start to see active errors because of the measurement operation or because of the gates before you reach this idle qubit windows. And one thing you can do to improve the accuracy of the model is to apply active error mitigation. And we particularly looked into two approaches. So to minimize errors, we use some calibration matrix-based error mitigation. And then to minimize gate errors, we use noise extrapolation. And there's some additional cost in terms of the number of circuits that you need to execute. And so with this experimental results, we generate different versions of our model, GNN model, one without any measurement feature, which is like the one that doesn't even require any interaction with the hardware. And then one that requires only measurements. And this requires very limited number of circuits to be executed in advance, just to approximate this amplitude of the qubit states. And then one that requires also applying active error mitigation to make sure that this approximation of the qubit state are accurate. So you can get rid of as much noise as you can, and this requires even more interaction with the quantum hardware. And then again, how do you define whether inserting a DD sequence is good or not? So you need to have a criticality threshold. And so you may say, when you look into the training data sets, if you inject a DD sequence and that gives any improvement, that could make the idle qubit window critical. We also consider those DD sequence that gives you 5% or more increase, because it's very often that if you execute the circuit many times, you can get a little bit increase or decrease in the output state fidelity. So what I'm saying is 1 or 2% increase doesn't mean that DD sequence is actually good. It just means that there's just an error fluctuation between different execution. And so one of the main things that we observe is as you increase the criticality threshold to, let's say, 10% or more, you get actually more improvements because now you're getting rid of these fluctuations. And then we consider different fidelity metrics. So I'm running out of time. So the first slide is just to talk about prediction accuracy. The takeaway message, regardless of the model, if you don't apply any measurement, yes, you get about 87% accuracy. If you conduct simple measurement, this can boost it up to 92. If you apply error corrections, then this goes to 99. But most importantly is what's the impact if you apply this model, like what's the impact on fidelity by SRGD sequence based on the model. And like I said, as you increase the criticality threshold to 10% or more, you can achieve up to 17 to 18% increase in the output state fidelity, which is quite significant. And you see that we were actually comparing against ADAPT and the noisy simulator. And these are ADAPTs and noisy simulators. And this gray line is just the GNN with active error mitigation and shows you how much increase in the output fidelity you can get. Okay, so I want to quickly wrap up the talk with some takeaway message. So the first one is it's really the time to contribute to quantum computing, regardless of your background, whether you come from the computer science or you come from physics or even computer and electrical engineering. The second message is NISQ systems are expected to serve as accelerators for very interesting applications. Deep learning is also very powerful, in particular for this on graph neural network, in modeling the reliability of NISQ systems. And these deep learning models can be smartly integrated with the quantum circuit compilation stack to boost the fidelity. I just gave you one example of doing that by mitigating idling errors, but we're actually actively looking into this and how do we leverage these data-driven approach to help us to maximize the fidelity of the quantum circuits. The last message, we are actively looking for students and collaborators, so feel free to reach out. Thank you so much, and I'll be more than happy to take questions.
Thank you so much, Samah. And let's see, Nirup, do you see any questions on Q&A, or should I start asking questions?
No, I think the Q&A is, we're still waiting for them to come forward with questions. I think we can start off with a few questions.
Okay, so I have a question, I think interesting insight. And how do you define this output fidelity in terms of error? You know, what is your, you maybe I missed it in the presentation, so could you shed some light on, you know, what is the evaluation that you are looking at in terms of measuring output fidelity for reliability?
Right. We just it's actually toward the end. So yes. So I guess the fidelity matrix depends on the application, right? There are applications that result in a single output. For example, the Grover algorithm, the BB algorithm, or even looking into small mathematical models, such as building an adder or a modular function. So these all evaluate to a single output. And so our fidelity matrix is simply, we will look into how many of these trials. So typically you take the circuit and you execute it for like around 10,000 to 8,000 trials, right? And you know what the expected output is. So you're going to compute what is the number of successful trial over the total number of trial. This is like one of the basic metrics that people were actually looking into when they build all these compilation stacks. But then if you look into applications such as, you know, QAOA, like solving optimization problems using hybrid, classical, and quantum systems, these algorithms do not evaluate to a single output. And the way how it works is you have to look into the entire output distribution to, for example, to maximize the cost function, right? And so for that, we use Hellinger fidelity. And I think this is kind of more useful metrics for near-term quantum devices. And so what we do is, because we're just trying to test, right? So we take the circuit simulated in a classical computer. Again, this is only for testing. The real scenario, you don't have to simulate anything. But once you simulate the circuit, you will get a distribution. And then we use this Hamilton fidelity, look into the distribution from the actual execution and the distribution from the simulation. You can see this formula help us to compute the Hellinger fidelity, like to compute the fidelity. We we actually use this Hellinger fidelity as well. And we did some analysis in which we say, if we can maximize the Hellinger fidelity, what happens to the cost function? So for example, when you look into optimization problems, yes, you will get a distribution for simulation and distribution from the actual function. But then eventually the output, the distribution output of the circuit will go to something we call it a cost function. And then the goal is, for example, I don't know, you're solving a max cut, graph max cut problem. And so what is the objective? You want to maximize the cost function. So the output of the quantum circuit doesn't give you a cost function. It gives you, let's say, a potential cut for the graph. And then you take all these different cuts and you feed them to the cost function and you see which cut give you the highest cost function. So what we did is we compare maximizing the Hellinger fidelity with maximizing the cost function. And we saw like there's some sort of a linear relationship. And that's why we don't look into application specific cost function, but we just compare simulation with distribution with actual hardware distribution. And eventually, if they are kind of very close to each other, we saw that we see that that also increase the corresponding cost function of a given application, such as QAOA and BQE.
Great. I think that just thank you for this detailed explanation. And is your team have worked with all these D-wave simulation, D-wave? I keep on hearing about this optimization framework from quantum inspired environment. So I was just curious to see what tools are you using, or are you also familiar with D-wave?
We haven't used the D-Wave because I guess we are not only interested on optimization problems, so we look into any potential application to quantum devices. So I think with these like superconducting and trapped ion, they're more like universal quantum device that can solve problems beside optimization. It would be interesting to study like the impact of these models if we apply them to D-Wave optimization algorithm versus superconducting optimization.
The reason I asked about that is because you talked about some decompositions of gates, and it's like there is a good element of optimization that this opens up some problems. I think that's interesting.
Yes.
And one other thing is, how has any work been done in terms of capturing the gate error characteristics versus the number of qubits, I'm just curious to see, because it's a small scale system, what you are sharing, I was wondering, I think that's what can you share about this relationship between, has any work on this gate error? I know you talked about this DDC sequencing, all mitigating that gate error things, but I'm just curious to see, are there any linear relationship or some kind of a functional relationship between the gate error characteristics?
Yeah. So just to characterize gate errors, we typically apply. You can use tomography or you can use the randomized benchmarking. So I think when they calibrate the hardware and they report these error rates, they actually specifically target randomized benchmarking. And so basically, let's say you want to study, let's say here, you want to study, I guess I don't have a quantum hardware. Let's say you want to study an error rate of a given C0. And so you're going to build a circuit that has many copies of this single qubit C0 gates, and then with different depth. With that only particular gates, and then you execute different version of it on the quantum hardware. And then eventually these circuits evaluate to a known output. And so you can take the average of the error rates of all of these different same C0 gates repeated multiple times to somehow approximate what error rates is. So one thing to keep in mind, you are taking the average of a C0 gate that occur multiple times. And that's one interesting problem, because also the errors of the gate depends on the circuit structure. So you're not only looking at the C0 gate in the middle of the circuit, you're just taking the average. Now going back to your question, the relationship between the gate count and the gate error, there is actually a metric. So IBM have, this is what they call it, quantum volume. I think they have it like 2 years ago or something, they proposed it. And this is kind of a metric that they use to assess the performance of the quantum hardware. Like you say, oh, I have 2 quantum hardware. One of them has a volume of 32. One of them has a quantum volume of 16. So the one with 32 is better. And the way how it works is they generate like some sort of random circuits where the number of qubits and the circuit depth is equal. And then they execute, as far as I remember, they execute these circuits and they have a threshold levels, right? So how much we can expand the number of qubits and the circuit depth to achieve very good fidelity. So when you say a quantum volume is 32, that means that you can have a circuit with 32 qubits and a depth of 32, and that gives you a very good fidelity. So I mean that's one metric they propose, but again, I think assessing the performance of the quantum circuit is by itself is an interesting area. So people also propose all different kind of things. And it just something came into my mind that so last year there was very interesting article where they actually have application specific performance measure. So it depends on what kind of quantum algorithm you're running. For that algorithm, it has its own methods to assess success probability, however you compute that. And they have like a bunch of benchmarks that they use, the same as a spec benchmark for architecture people, right? They have all their own spec benchmark to evaluate performance of different hardware. And so they also created a spec benchmark. They made it publicly available and say, okay, we can use these spec benchmark, run it in ion traps, run it in superconducting or whatever quantum hardware to evaluate the performance of these hardware and accordingly select for a given application which device I should use. So they're not using quantum volume. They're using application specific. And I think that should be the way because—
Thank you.
Yeah.
Thank you so much again for providing a detailed insight. I appreciate it. Arup, do you see any other questions?
Yeah, we have one
Do you have
question
any
in
questions?
we have one question in the Q&A. How can we automatically handle many intricacies of NISQ and get a better understanding on noisy errors in quantum circuits?
That seems like a broad question.
Yeah. Well, I guess looking into NISQ and its application versus noise, they're not actually two separate components. So like, let's say if we're looking into optimization problems, right? Like QAA and BQE. So one major challenge is that, okay, how do you specify the parameters of the circuit in order to minimize the, to maximize the success probability of the circuit? Now, if you think about hardware error, what people now recently, like I guess last year, started to think about, instead of just when you build the algorithm, right, and you try to determine the parameters of the gate, and instead of just thinking about noise-free idle scenario, and you try to say, oh, how do I specify parameter to maximize success probability? Now you have to take the error rates into account. And now tuning the parameters of the gates is actually to both eliminate errors as much as possible and also evaluate to a higher, I guess, success probability, or in terms of optimization problem, higher cost function. So I think you have to mesh them together. They're not two separate things depending on the applications. And so currently there's all this interesting work for tuning parameters to both the tuning parameters of the gates of optimization problem to both maximize cost function, and eventually that means minimizing errors. So
great. Any other questions? If not, I think thank you, Dr. Samah, for your time.
yeah.
And so grateful for your presentation. And this recording will be made available online and sent shortly. Purpose. And also we'll send you a nice bag and certificate signed by our team, and appreciate for your time and effort in preparing for this presentation. I look forward to working with you in the future, and again, thank you again.
Thank you so much. Thanks.